Okay. So as I mentioned in a few of my announcements, today we're done with part one of the entire course. So we divided the course into three different sections. The first one was mostly based on search algorithms, where we talked about the deterministic environment and applying several search algorithms on the environments where we said that the environment is known. We know what actions your program, your agent can take, where the goal is, and how to proceed in the in the search environment that should just provide you the least cost solution. And the entire idea basically was to do planning or pathing, like find the path that with the least possible cost, right? So we talked mostly about the deterministic environment, where we knew the environment, we knew the game's structure. For example, maze, like Pac-Man maze, we knew like how the maze looks like, and then based on the structure of the maze, we did some planning and applied several algorithms, right? And also traveling Romania problem, we knew a heuristic, or we knew the cities, their connections, like straight line distance, et cetera, et cetera. And then we said that, okay, let's find the shortest path. And then we created in the entire tree structure. And then we would just expand the nodes with the least possible cost. And at the end, we will find out the path to a goal that provides us the least cost. So today, we're going to talk about something different. This is the start of the second section of the entire course, okay, where we're going to talk quite a bit about the actual, not actual real world environments, but the environments where we don't know the environment, okay? The scenarios or the problems where we don't know what the environment is. There might be a goal state, there might not be a goal state, okay? So in this section, we're gonna talk quite a bit about the probability, okay? Because the environment may have uncertainty. As we said, that the actual real world environment is quite complex. It's it may have some uncertainty, because we might not know what's going to happen, even if we are given a set of actions to choose. Okay, so today we're going to basically talk about Markov decision processes. Okay, so in general form, we're going to talk about Markov processes. Okay, both Markov reward process and Markov decision processes. Okay, one thing that you will have to remember about Markov decision processes: every time you talk about Markov decision processes, we're going to talk about non-deterministic search. So MDP basically is a non-deterministic search, search algorithm. All right. So MDP, we're going to consider non-deterministic search problems. We're going to implement, a search algorithm that basically, or we're going to transform several real-world problems into MDPs, and then we're going to talk about how to solve them using MDPs. And at various places, you will realize, or you will notice, that it is very similar to ExpectMax that we have done. That includes, involves probability, calculating the probability at every step that we're going to take. But in addition to that, we're going to basically consider the reward, how we embed or incorporate the rewards at every step. Okay, and we will also talk about, not the plan, because in our other, game scenarios, Pac-Man or traveling Romania problem, we talked about basically finding the best possible route, right? So we did planning, or we did pathing. Here, we just simply don't have the plan. Okay, why? Because as I said, that the environment is uncertain, there is complexity involved. We are given a set of actions, okay, at every step as a software agent, program that you have written, or the system. You are given a set of actions, but you can take one of those actions. And our job in this entire course is to, take certain actions that should maximize your expected utility, MEU, right? We will come back and forth again and again on this term, because we're going to design agents that will maximize their expected utilities. But what in non-deterministic environment, what we don't have the control over is that we can still take the action, but we are not sure if we are going to be in a state that is intended, that we intend to be in, because the environment plays a role in, because there is uncertainty. Okay, we're not sure. So we covered an example, but before I explain the example, Ronald.
There was this expected uncertainty.
Maximum expected utility. So we should maximize our expected utility. Okay, and I'll also talk a little bit about why we say expected utility. Okay, expected basically is the average or weighted average over, a set of actions or set of state and action pair that we're given, we're provided, and we're going to talk about maximum expected utility. Today we're going to cover something very important that is going to basically take about 2 to 3 weeks. Okay, we're going to talk about the Bellman equation over and over again, because this is basically the actual core and crux behind MDP, solving real world problems using MDP, and solving real world problems using reinforcement learning too. Okay, so we're going to look at that. We won't have the plans anymore. What we will have is a policy, a recommendation basically for the agent or the program. Like, okay, if you are in a certain state, take this action that the program believes that will provide the maximum expected utility. So that's actually a policy. All right. So no like solid plan, because we're not sure about the environment, but we have the policy, a kind of a recommendation at every step. So we will talk about that quite a bit. Okay. So one thing is that we will cover non-deterministic, search problems. So what we did in our search problems for the first, it should have been 4 weeks, but we have spent 5 weeks, right? 5 weeks because of the flood and a day off too. All right. So in planning, we said that we knew the environment, right? We had the structure of the maze, or in traveling Romania problem, we had the cities, adjacent cities, et cetera, et cetera. We had the heuristic. So in that case, our environment was kind of fully observable, because we did not think about like, okay, if I'm expanding a certain node in a tree, I'm sure that I'm going to get to that. Okay. So in that case, we were basically, dealing with a fully observable environment, and we were deterministic. And our job was to basically find the path, right? Sequence of actions with deterministic consequences, right? We basically were supposed to find the path in all your search, problems that you're working on as your homework one activity. You basically return a path. Basically at every step, take an action, expand which node out of given, given possible, choices, which node to expand, and then just move forward, right? We were given a complete path. Here, we're going to start talking about a kind of a couple, or at least 2 or 3 examples today using MDPs in terms of the real world environment, okay? Real world environment, and a very simple, basically, scenario that we talked about in week 1, very first lecture, that we're going to design agents basically through their sensors. The agent is going to perceive the environment, okay? Perceive the environment, and then using actuators, basically perform some actions in order to, achieve a certain task. And those actuators are going to basically perform, like some actions given some of the knowledge that we are going to build in here, okay? So that was the entire, basically, overall big picture of the design agent. And this is going to be the figure that we're going to follow for this week and also the next week. So for reinforcement learning and MDPs, we're going to talk about that. So the first example that we're going to cover basically is again a maze-like problem that we have, but we're just going to talk about basically, a robot or an agent that basically lives in that grid world, lives in that maze, and just likes to move around. And there are certain rules that we will have to follow, okay, in this game scenario. Something like this. So you see here, so, here's a very, very simple, maze world. By the way, we're going to start with a fully known, environment, fully known maze world where we know where the walls are, where basically our reward is, and where there might be a penalization. So we're going to talk about a few of those things. But the basic idea basically is that there is an agent that we have, all right? it lives in a small grid world and likes to move around. There are, walls around basically in the maze, and there are some of the, like walls within the maze too that actually block the path of the agent. Okay, and we're going to talk about, like a little bit more in terms of the logic that is involved in it. So now in search problems, we have covered basically expect-max search, right? We said that with certain probability, we can take a certain action, but nowhere we talked about the reward. Okay, nowhere we talk about the reward. What we talked quite a lot about basically is the least cost, right? What is the minimum cost that is going to, that we're going to have to pay to expand a certain node? So in here, basically, we're going to talk about the reward. How many points do we get after taking every step within the environment? Or how much reward does this little, agent get after taking every step within the maze? So reward, you can kind of, think of in terms of the negative cost. Okay, so the higher the cost basically is, the lower the reward, right? So we can talk about basically the reward, and I will talk about that in a little bit more detail. Is the reward we can consider for now is the negative cost. So the lower the cost, the higher the reward that we will have. Okay, so what we do is there are certain areas in the grid world where basically the game ends. Something like this. The agent basically is told that if you get to the top right square or top right, cell in the maze world, you're going to get a reward or you're going to get a diamond. And that's the highest reward that you have. Okay. And then if you end up, falling in the middle to the right most, it's basically, it's a fire pit. You're just going to, fall into fire and your agent will be destroyed or your robot will be destroyed. So what we will have to do is we're going to solve that problem using non-deterministic search. And what the difference between non-deterministic search and search is that in non-deterministic search problems, as I just said, that we are given a set of actions. We can take those, one of those actions, but are not going to be 100% sure that we will be in a state that we intended to be in by taking a certain action. Something like this. So you see here, the agent basically is planning on moving north. Okay, moving north. In search problems, what we did was expand the north node, and there's 100% probability that we are going to get to north state. But in expect-max search, we said that using expect-max, we can take an action. We can wish to expand the north node or go north, but we're not going to be sure 100% that we are going to go north. Such as we said, I gave an example of a robot that you build, assemble, and that is just going to basically walk in a free environment and just move from the start to a destination. But there might be, wind blowing it away to the right, to the left. There might be a puddle, a hole in front of it. It will have to change its way. Or, if you're traveling from Arad to Bucharest, you take an Uber, but who knows that there might be an accident in Cebu? Who knows that there might be landsliding in Cebu? You might miss your flight. So those were actually the environmental, actions or environmental states that were out of your control. You can still take an action that you think that it is going to maximize your expected utility, but you're not going to be 100% sure that you are going to get the reward or you are going to get into a state that you intended to be. So what we do is, what we're going to have is, we're going to have a, just like how we did at each arc, just like in expect-max, there is a probability involved. We say that, 80% of the time, the agent wants to move north, it actually will get to north, 80%. But there is a 10% chance that it might just, go right clockwise, go east. And there is a 10% chance, even if it wanted to move north one step, it might just go west. Okay, so this is basically the probability or the uncertainty that we will involve in it. So intended action A, just go north, but there are certain probabilities that are involved. That is where we're going to add the uncertainty or add the probability. that is going to look very similar to expected max search. Okay, what we did not have in expected max search was basically the rewards that we are going to receive. So every single time, as I just said, that if you go into the top right as an agent, the agent basically will get the highest possible reward, +1. Okay, so that basically is the big reward. When you end the game, when the game is finished in the intended state that you want to be in, you're going to get the maximum or the biggest possible reward of playing that game. So that's one, okay, big reward that comes to the end. It can be a good reward or it can be a bad reward, because even if you are in this square, there might be a 10% chance that even if you want to go north, you might end up just, falling in a fire pit and basically destroying your robot, right? So there might still be a chance that you might have a negative reward. Our job will be to maximize our expected utility. So we have big reward that we get at the end, and then we will have the small living reward at each step. Every single step, just like how we said in the Pac-Man game scenario, right? Every single time we basically like walk in the maze, if we don't eat the dot, we're going to get a score of -1, right? If we eat the dot, we're going to get the score of 10. We had something like that, right? And then we had the value of the game. But what we did not include was the small living reward and the big living reward at the end. And we did not actually mention in the expected max search, when we expanded the tree, nowhere we mentioned where those rewards are. All what we had was basically the value at the leaf node or at the terminal node, right? So that's what we're going to talk about today, how we can embed basically those rewards. And our goal is going to be to maximize the sum of the rewards that we're going to have. Okay, the sum of the living rewards that we will have, we will maximize that. So in deterministic grid environment, what we did was we said that we start with the tree, right, with the root. Our intention is to go north, right, step away from the fire, right, go north, and we take that action and exactly that same in search problem, right? In deterministic search problem, we said that there was a 100% probability if we are going to expand that state or if we are going to go north, we're going to go north. Good. In expected max search, we talked about like even if we want to go north, there is a certain probability that is involved. We either might go north with 80% probability, or there is a 10% chance that your agent's foot might slip and it will just fall in the fire pit, right? There's a 10% chance, and there's a 10% chance that the wind might blow or it might slip towards the right and it will go to the right. So that's what we had in an expected max search problem, right? So we had like probabilities involved with or given at each of the arc that we have. So that's called basically the stochastic grid environment or stochastic grid world, where we do have the uncertainties involved. So we're gonna basically extend our expected max search a little bit by adding the rewards, and then we're gonna talk about this magical equation, Bellman equation, that we're gonna discuss and see how that plays a very important role in solving non-deterministic or stochastic search problems. Ronald.
So the stochastic has the expected uncertainties. So just said, or has the expected?
We do have uncertainty in stochastic. So in stochastic, we have uncertainty involved. We're not sure that the actions we're going to take are going to take us to the intended state that we actually want to be in, because there is an uncertainty. There is a chance node that is involved. That is what we also talked about in the expected max search algorithms too. There's a probability involved, and that's where we're not sure of the action that we're going to take is going to take us to the intended state. Okay, so in stochastic, we have the probabilities involved, and we will have to solve using probabilistic approaches. But in Expectamax, as I said, with that we did not have rewards included. So in most of the MDP problem, what we're going to talk about for this week and for next week is actually very similar to Expectamax search, but then we're also going to add the small living rewards and also the big reward at the end. So we're going to expand our Expectamax search algorithm to, MDPs using the reward function. So Expectamax, in Expectamax, we had chance nodes, right? At each chance node, there is a probability that we might end up in a certain next state of the environment, right? And then a certain next step. But what we did not talk about in the Expectamax search was that we did not, discuss any reward. Is the agent going to get any reward or not? All what we talked about is that how to expand the least possible cost solution or path, right? That's what we have. What we did not have is that every time we take a step, how does the reward play, a role in the environment? So that's what we're going to talk about in more detail. It will get clear in a few minutes. Okay. So what we have is in here, or even in search problems, we're actually kind of building the brain for the agent, right? Like to either search for a path, right? Plan, or planning or pathing. And here, we're also basically building the brain for an agent so that it interacts with the environment and tries to maximize its expected utility at every possible step. So we're basically, what we do is we formally describe an environment for reinforcement learning. So MDP basically, once again, I said in the announcement also that MDP basically is the building block or is the first step to formally describe in the environment for reinforcement learning, because we will see and we'll talk about Bellman equation. And then we're going to talk about a new state in our search problem today. That is going to be the, something that we're going to continue talking about this week and also next week, okay, multiple times. So we're going to start with the environment that is fully observable. We're going to have the states that completely characterize the process. I will talk about that in much more detail in the coming slides. The good thing, the beauty of MDPs is that they can solve all possible real world problems as long as you can formulate them into an MDP. Okay. Quite mouthful. We're not going to be able to understand until we solve a couple of problems today. So we're going to talk about, the real world problems, and then we're going to see how we can transform a real world problem, even a real world continuous problem, not the discrete problem, a real world continuous problem, and solve that using MDPs. Okay. So before I go into the details of that, we're going to talk about basically, what describes the MDP. So we're going to have the set of world states exactly the same as the search problems that we had, like the state where in the maze world, we can say the state is basically our current XY position. Those states that we're going to have in the maze world, right? We're going to have the set of feasible actions exactly the same as how we did how we covered basically in the search problems, like can go north, south, east, west, set of actions, perfectly fine. We had the successor function, right? In search problems. The successor function basically was giving us an action or, a node to expand in the search algorithms, right? Or we had the state action pair. Right, in the search problems, we had the successor function. What we're going to do is here, we're going to basically unpack the successor function to add one more item today was actually the reward function that we're going to have. Remember in the Expectamax search, we said that instead of min and max functions, we're going to calculate the probability, weighted average, P times V, the value, right? So that's what we had. The probability function, we have the probability that is associated with each of the arcs, right? And then we were basically calculating or computing the probabilities at every step. So in MDPs, we're going to have the probabilities from like at whichever state for every single state in your environment, in a fully observable environment, there is going to be a certain probability that you can go into one of the next future states. Okay, so that is going to be the transition matrix. So what does it have is that we have state, which is S, the current state. You can take an action, okay, either north, south, east, west, and then it's going to basically take you to a new state with a certain probability, which is basically our transition function. So it's kind of a lookup table, okay? So we're gonna have a matrix, a lookup table, where every row is a possible state that you can be in and that you are in, and every column is a possible state that you can get into, okay? So it's like a lookup table, and we will see how we can build this transition matrix. And it's going to have three important elements: the state at which you're currently at, okay, the actions, the possible actions that you can take, and then the new possible state that you can get into by taking a certain action. So you're going to have three possible elements, and it's kind of just like probability that an action from S leads to S prime. And we're just going to denote it with a probability of, getting into a future state, into the next state, S prime, given that you are at a certain state and you can take a certain action. It's like a conditional probability that we're going to. So we're going to build this lookup table that is going to be very similar to the probabilities that we covered in expect max search. But what we're going to include today is actually the reward function. Okay, the reward function. And we're going to talk a little bit more about the reward function, in the coming slides, how we can embed that to expand our expected max search into a complete MVP. We have a start state, right? Like in a maze world, your robot or your agent basically is standing somewhere where you want to start, playing. So you have a start state. You may or may not have a terminal state. Okay, you may or you may not have the goal state. The goal state basically is to exit and get the maximum reward, right? As we said in the maze world, the top right cell. That's when you get there, the game finishes because you get the maximum reward. That's what your goal was. But it might not always be possible that you actually get to the goal state. You might fall in a fire pit. 2, the game ends, but you haven't reached the goal state, right? So you may or may not have the goal state. So let's before I talk about the MDP, how many of you have heard of this guy named Andrei Markov? Andrei Markov. Okay, so he basically explained a very important concept that is of a paramount importance in games or scenarios or problems of probability. That includes probability, involves probability, because without this property, we will see it's difficult to impossible to solve real world problems if we did not have this property. So it's actually pretty simple. All what Markov property says is that your future is independent of the past given the present. So only the current state and action matters for taking a decision. What we do is that if you start basically, the grid world, maze environment. So your agent moves, randomly or with a certain policy that you have in an environment. The probability that you take basically, a certain action at that current state is independent of what you have done in the past. Okay, so suppose that my job standing here is to exit this room and get the biggest, possible reward. If I'm actually at the, in the middle of the room, my action basically from taking the step from there is independent of when I was here. So my future is only dependent on the present, and we can throw away all the entire past. Okay, so something like this, you see, it's basically memoryless. Suppose that you are at a current state S, S of t, okay, at the current time. At the current time, you're in the current state, you take a certain action, AT, all right? Given that you have completely, traversed the entire path from the beginning of the game, is only dependent, so your probability of going to the next state, ST plus 1, going to the next state is only dependent on the current state and action that you have, and you can basically remove or throw away the entire past, which gives us this beautiful equation that our next state, okay, is only dependent, or our future is only dependent on our current state, our present. And you will see this, basically the application of this equation in this week's lectures, and also reinforcement learning. And we will also talk about, how useful this property is when we're going to talk about solving some real world problems. Okay, how this can reduce the complexity, because you see it says memory less. Okay, so we're going to talk quite a bit about the Markov property, but let's start basically with this equation that we just talked about, right? So the probability basically that you go into the next state at time t plus 1, which we denoted as S prime, given that you are at the current state t, like we just, let's say the first step, and you take a certain action, is only dependent of the current state. Okay, from t, like from time t, current time, to the beginning of the problem is only dependent on the current time t. So let's see how we can build basically the transition matrix that we have. Remember we said that in Expectamax we had something like this, right? Expectamax search. So we had the maximizing agent, and then we had the chance nodes, and then there was a probability that was associated with each of the edge, right? And then we had maximizing agent, once again, something like this, right? We're going to talk about how we can take these numbers and basically build this transition matrix. It's like a two-dimensional array that we're going to, it's another data structure that we're going to have to maintain. So in your homework 2, in Expectamax search, you're going to use some built-in functions of the Pacman scenario. You will not have to worry about how you're going to basically pick the probability from this transition matrix. It's already implemented. But we're going to talk a little bit more about how this transition matrix is, is actually built or created using, a couple of game scenarios that we're going to talk about here. Okay, so we're going to see. So what it has is, at every, as I said, every row basically is a possible state that you can be in, and every column is actually a possible state that you can get to from the current state. In this, remember, is if in Expectamax search, we may have non-zero probabilities, or we may have a probability 0 too, right? So if there is a probability 0, that's fine. It's because at that current state, you're just simply unable to take a certain action, something like this. So your agent basically can be in this situation. In here, there's nothing. There's a wall at the top. You cannot take north, further north. So there's going to be a 0 probability that you're going to make any progress if you try to go north, because you're going to hit the wall. So probabilities can be 0 too. That's fine. All right, let's get to the actual also the total reward. We're going to expand this equation quite a bit. Okay, quite a bit. The bottom equation, basically that's the big reward that we're going to have, right? And then we're going to talk about the living reward at every step. We're going to talk about the expectation, or how we're going to basically expand that formula that we had in the Expectamax search. Okay, enough talking. Let's talk about the example. Suppose class dynamics example. Suppose that we're in this class, okay? And the requirement for this class basically is that you have to take 3 of these next classes to pass the reinforcement learning part. Okay, class 1, class 2, class 3. All right. If you take all 3 classes without sleeping, without missing the class, then you're going to pass. Okay. Within that, like in our classes, we might, you might get bored. There might be, several equations that we might talk about, and it might just like, kind of get you bored, and then it might let you just like use your social media for some time, either on your laptop or on your cell phone, which is why I always say no devices in the classroom. But you may just go to Twitter or Instagram or whatever social media that you like, right? During the class, you might fall asleep too, a little bit. Suppose that the class 1 was just, an introduction class, and it was not that hard. From Wednesday, what we're going to talk about is we're going to talk about quite a lot of equations, quite a lot of like intense, messy stuff, which is why I've been saying these 2-3 weeks are extremely important. Please stay, like if you don't understand anything, if you feel, tired a little bit, we can even stop and give it, some time, but like stay there and not try to fall asleep. When you pass, you can enjoy, you can have fun with your friends, and you can go to the bar and say like, I did a really good job and I passed this module, or even this entire course, right? So let's try to talk about, how we can create basically a transition matrix from this real world environment, right? We have talked about the real world environment. And I also said that MDPs can also solve real world environments in which there is a continuous variable that might never end, right? Something like this. So we now have arrows, right? So we're in the class 1. So we start from there. We're in the class 1. If you do well in class 1, you can go to class 2 with a certain probability, right? From class 2, you might fall asleep for a bit, or you can go to class 3, right? From class 3, you can pass, and then once you pass, you can go home and have a long, like nice, good sleep. Or from class 1, you might just feel a little tired, a little bored. You can just start using Twitter, and you see there's a loop on Twitter too. This one. The reason why is because if I continue talking, you might continue getting bored, more and more bored, and you might basically continue using Twitter for the time that you just, you're unsure of. So that's where the continuity comes in. MDPs, like, you can probably keep doing something for an indefinite amount of time. Just like something like, in the maze world, if the agent basically hits the wall, it can keep trying, to hit the wall and will never finish or will never end the game. That has something to do with basically the reward function, or the reward that we're going to have. That we're going to talk about that in just a few minutes. But this is something that we can transform our real world problem into an MDP. And how we can create the transition matrix from this, all what we will have to do is, as I said, it's a transition matrix. We can have class 1, class 2, class 3, Twitter, right? You can pass, you can sleep, and you can go to the bar, right? And then we can also have the same thing, C2, C3, Twitter, pass, sleep, or go to the bar. Go to the bar. And where do those probabilities come from? Something like this. In an observable environment, or in an explicit policy, explicit plan that you have, or a strategy that you have, basically you come up, or based on your domain knowledge, you can have some sort of probabilities like that. Suppose that the class 1 is, like fair enough. There is a 50% chance that you might, pass and go to class 2, and there's a 50% chance that you just start using Twitter. So that's based on our, like experience, knowledge that we might have. If you don't like this class, class 1 enough, then there is a very high probability that you might continue using your social media in the class. And there's a, lower chance basically that you might, get back to the class. In class, in certain classes, you might fall asleep too. So this is basically that you transform the entire environment or your real world problem into an MDP, and then you assign probabilities. all what you will have to do is take those numbers. Let me just erase it. Take those numbers and put it into a matrix. That's your transition matrix. Okay, remember we said that we have T, S, A, S prime. Your S basically is any of this, T of class 1, you take an action. So let's say you really want to go to class 2, right? A1, let's say this is your A1. And then you can go to class 2. And what is the probability for that? You see here, you're in class 1, you can take a certain action and you can get to class 2, which is 0.5. Right? Simple, straightforward. Simple enough, right? We just have a two-dimensional just matrix, transition matrix that just gives us the probability. Those probabilities, like some of the rows, some of the entries in that matrix can be 0, 2. That's okay. Because from class 1, you cannot jump to pass right away. So there's going to be a 0 probability for that. And remember the second law of probability that we talked about in the last lecture is that the sum of the probabilities for a certain state from taking all possible actions, it has to be equal to 1. So the sum of every single row in here has to be equal to 1. So we're following the second law of probability here. All right? Clear enough so far? Okay. So I'm just so C1, C2, C3 are class 1, class 2, class 3, and then class, bar, Twitter, sleep. Actually, I either talk about Facebook or Twitter, Facebook or sleep. So all what I'm doing is I'm just mentioning these. Okay, C1, C2, C3 are the classes. The rows are the state that you can possibly be in. Okay. And the columns are the possible states that you can get into from your current state, from the state where you're at right now.
So these are the goals?
No. So suppose that you're in row 3, which is C3. Suppose that you're in C3. What can you do when you are in class 3? You can either you can pass or you can go to the bottom. Look at these arrows, right? You see there is a 60% chance when you're in 3, you can pass or you can go to the bottom. And the sum of those probabilities is equal to 1. That's what I meant.
Okay, so goals.
Right. So remember this equation. This is going to be very important. The final big reward, and we're going to talk about that. And we're going to talk about how basically we are going to get the rewards, immediate rewards, how far or short-sighted we can be in just a few moments. So let's talk about the policy first. Remember we said that in search problems, we have an actual plan. Here we just have the recommendation. If you look at the same maze grid word that we talked about, so these arrows are simply recommending the agent basically to go in a certain direction. Okay. So there can be multiple plans. There can be multiple plans, something like this. There can be another plan in which an arrow is something like this. There can be another plan, another strategy, another policy in which the arrow can be like this. There can be multiple strategies, there are multiple policies that we may have. What we will have to do is we will have to choose the policy that maximizes our reward, that gives us the best possible action to take at every step. At every state, right? Because that best possible action is going to give us the maximum possible reward at the end. So there can be multiple policies, but remember in MDPs, we're going to have a policy. The star, why I'm mentioning the star in here, it's because it denotes the best policy possible that we can have. That is going to give us the highest possible reward. And we're going to denote it with pi. Okay, So for these 3-4 lectures, we're going to denote it with pi. Now, let's talk about, optimal policies. We can, the balance between the risk and the reward changes depending on the value of reward. How can we set the value of the reward? What happens if you set the value of the immediate reward really, really low from the final reward? Or what happens if you set the immediate reward really high compared to the final overall reward? What happens? This basically gives us a little bit of an indication of what the optimal policy should be, okay? There are several ways to, find out the optimal policy or find out the optimal, set of reward values that we can. Now, suppose that, in our overall reward is +1 and -1, right? In here, or -1, overall final big reward that we can have. Suppose that we set the value of the reward, the immediate reward is -0.01, which is kind of really low compared to the big reward. What happens? Look at those arrows. As soon as it gets basically closer to this part, it tries to move away. It tries to move away. The reason why is because our final reward function basically is our t plus 1, basically getting a reward, plus I'll talk about what this gamma is, r t plus 2, and all the way to the future. So the final reward basically depends on the immediate reward that we get. So if the final reward basically is too large, okay, too big compared to your immediate reward, then that means basically when you put that into the equation, it's going to tell you when you are in that step to try to stay away from that final reward, because immediate reward is extremely small compared to the final reward. And just because you have all the time in the world to just move in the maze environment, as soon as you get closer to the final reward, you're going to try to stay away. Now you see in here, you can go west, but it's not going to do anything for your agent, right? It's not going to do anything, but it will still try to hit the wall to try to stay away from the big reward, because your big reward is way bigger compared to your immediate reward. Okay, if you have slightly better, minus 0.03, then basically, you can get another policy, another recommendation. If you have another, like, let's say minus 0.4, then you can have another policy, and it's going to tell you that, okay, if you're on this edge, you can take east. If you're on this edge, you can take north and get all the way closer to your positive edge. And let's talk a little bit about how we calculate these awards. Now you see here, Nathan, just give me 1 second. You see here, if we keep the reward to -2, which is even much bigger than the final reward, big reward that you have, even if it is in here, it's going to say that my final reward is actually much lower than the immediate reward that I'm getting. Immediate reward that I'm getting, if I go this way, I'm not going to get a specific reward because I'm stuck, right? If I go this way, I'm getting -1, which is better than -2. So I just might end up dying, right? End up just basically going into the fire pit. So the reward basically really depends on immediate reward depends. Your final reward depends on the immediate reward. Yeah.
So these policies, we're assuming we're having non-deterministic meaning.
Right. We started talking about the fully observable environment at this moment. So this maze basically is fully observable. All what we're trying to do is we're actually working on an expected max search with the probabilities, but we're incorporating rewards. We're incorporating rewards right now. So I think in the previous slide that I have in here, yeah, what I forgot to tell you guys about, that we have a transition matrix, and then we also have a reward function. So at every step, now you see here, if you're in class 1, there is a 50% chance that you get to class 2, but then you're going to get the reward of -2. These rewards can be negative. That's okay. That's okay, right? Because we're not talking about the least cost possible solution. You can get a reward of -2, but then look at the final reward that you have. Final reward is going to be much larger than the immediate rewards. Okay, so we're going to talk about using another example that I have. Suppose that you have a, racing car, okay? Your robot racing car. And the job basically of that robot racing car is to, travel far and travel quickly. There can be a few possible states that your car can be in. Your car can just remain cool, or it can just get warm, because if you continue driving it really fast, it can get warm, or even it can get overheated. So these are the three possible states that you may have, right? And you can just have two possible actions. Let's say you can drive slow or you can drive fast. Now, for you, it might be a different, continuous probability, like, oh, drive, what do you mean by slow? That is it on a 60 miles per hour road, are you driving like 40 miles an hour? Is this slow for you? You can have different states, that's okay. But to keep the problem simple, let's just say we're driving either slow, there's a certain magic number, below that number, we're driving either slow or we're driving just fast. Okay, so these are the two possible actions that we can take. All right, going faster gets the double reward. Okay, so if we drive faster, because our job is to travel far and travel quickly. So if we drive faster, we get the double reward. So let's see how we can basically transform it into an MDP once again. Second example. So suppose that you are in your cool current, cool state on the bottom left on there. There is going to be 100% chance if you continue driving slow, you're going to just, your car is going to remain cool. So if you're driving slow, basically you're going to get a reward of 1. That's 1. From slow, if you drive fast, there is a 50% chance that your car might get warm, but you'll get the reward of 2 plus 2. And there's a 50% chance that your car might still remain cool, fine, because you're not sure if you're driving slower, for how long you're driving faster, right? For how long you're driving faster. So there's a 50% chance that your car might still remain cool with a reward of plus 2, right? Just look at that, look at those, requirements that I have. So now from the warm state, if you drive slow, okay, there's a 50% chance that your car will just get back to normal condition with reward plus 1. But you're not sure, depending on how long you drive slow for, there's a 50% chance that your car might still be in a warm condition with a reward of plus 1. And if you continue driving faster, then you're in trouble. You're going to get the reward of minus 10. You're going to destroy your car. Okay, overheated. How with expect-a-max search we solved this problem? Basically, we said at every, we had the maximizing agent, right? There's a chance node that we can either, from slow, you see here, from cool, we can drive slow, and then from cool to warm, we can either, we can drive fast, but we can remain cool or just get warm, right? Something like this. We create the tree. So if we keep driving slow, we'll be fine with 100% probability. With 50-50 probability, we can either remain cool or we can get, warm. And we just build the tree, right? With expect-a-max search, we just build the tree by using the probabilities. Have we talked anything about the rewards in expect-a-max? No. So the question is, where do those rewards get in here in this tree? That's what we try to solve in MDPs. Okay, and that's going to be the fundamental basics of reinforcement learning. How do we do that? Now we don't have the state action pair anymore. We have state action and we have the Q state. This is something that we're going to talk about, for a lot of times in MDP. So what we do is, remember in expect-a-max, we are in a current state. It's a maximizing agent. Perfect. Sounds good, right? Then what we do is we take an action, right? But then we are not sure we're not 100% sure that if we are going to get into the state by taking an action that we intended to be in. So we had the chance nodes, right? Probability nodes, something like this. Right? Probability nodes that we had. So what we had was, we had the value associated with each of the chance node also with the probability, right? Weighted average. And what we are doing in here at state S, by taking a certain action, we are getting into a new state. But according to the definition, what we're talking about is that we have to maximize our expected utility, right? Maximize our expected utility. So aren't we supposed to take an action that gives us the maximum of these utility, right? The maximization agent. Remember what we were doing was using the maximum function, right? Max function. We're going to get to a node that gives us the maximum value out of these possible, out of these average. Does that ring the bell that we had the maximizing agent, the facing up triangle? It was basically getting the max from these, right? So we had the values associated, propagated, and what we were doing was maximum of these values, right? In here, we're using the maximum. But when we are in here, we're not sure if we are getting into the S prime. We're not 100% sure. What we were doing was, in here, we were using weighted average, right? We were using weighted average in here. So remember these two steps. These are going to be extremely, extremely important. When you are at a state, you took an action and you can get into any possible, states like state, action. You can take action 1, action 2, action 3, action 4. You are going to pick or choose the action that is going to give you the highest possible reward out of those selected or possible choices that you can make. So you're going to use the max function there. And then down there, you're going to use basically the average, weighted average. And we're going to use the transition probability. Remember, we said that the value from there is going to be equal to P1 times V1, P2 times V2, et cetera, et cetera. So we're going to get, according to the transition probability that we're going to have. So here, this equation, you're seeing gamma in there. Okay, let's very briefly talk about what the heck is gamma in this equation. It's basically a discounting factor. It ranges from 0 to 1. From 0 to 1. It actually tells us how far do we have to look in the future. How far do we have to look in the future? So, steps, like let's say, my agent is standing here and the job is basically to get exit this door, right? So when we are planning, when we are getting the value of the game, should we just look all the way in the future that say, if I take step 1, where do I get? Then I take step further from that step. So I look all the way in the future and then see, what my value is going to be. So the further you look in the future, the better basically your goal was in your search problems, right? Here, now suppose that if I tell you that I'm going to give you $1,000 reward now, would you like it today? Or would you like it after 5 years from now on? Would you like $1,000 today or 5 years from today? Today, right? Shorter rewards are possible. Not shorter rewards are possible. Shorter term rewards are more desirable by humans. That's basically by nature. What if there's a very high interest rate, by then, and $1,000 does not mean as much as $1,000 means today, right? So as humans, we tend to have shorter term rewards, or we tend to prefer shorter term rewards as compared to longer term rewards, right? Second thing is that if you have a longer term reward, if you look at this equation, if you put basically, GT in here, RT plus 1 plus, you see gamma, RT plus 2 plus gamma squared, RT plus 3, and so on and so forth. And if you basically formalize this equation, it gets into this equation. So you see, every time you're multiplying gamma to multiplying your reward with, with a certain exponentially increasing gamma, right? So if you have gamma much, much larger, close to one, then that means you're actually running into infinite cycles. Remember, we had Twitter, a cycle on Twitter. Suppose that if we had 100% probability, this equation will get longer and longer and longer and will never finish. So having shorter gamma or discount factor basically is also beneficial and convenient to solve the mathematical equations in MDPs. Because you see, every time it's just basically getting, so gamma, let's say if gamma is 0.9, then gamma squared is going to be 0.81, right? Gamma to the power 3 is going to be 0.9 times 3, which is 79, 69, something like that, 0.69, something like that. So if you have the value of the gamma lower, let's say 0.5 or 0.4 shorter, then that means you're basically not being so far-sighted, but you're going to end up basically, breaking cycles in your MDPs, which is why MDPs can also solve continuous problems too by setting the value of gamma. So also, as you look further in the future in real world scenarios, the world is complex. There is uncertainty. You're going to have, more and more uncertainty about the environment, which is not going to be great for solving the problem. But let's say if you set the value of gamma to zero, then that is your basically the shortest possible sighted. You're not looking at any of the future. All what you're looking at is the reward for getting into the next stage. That is it. You're just only looking at one step further, one step ahead in time. So gamma decides how many steps ahead in time you can look at, or you're going to look at, depending on what problems you're trying to solve. Okay, so gamma is going to be very important, and it's going to be called the discounted reward. I wanted to show you the rewards. Let's say if we are basically setting the value of gamma to 0, what happens? Remember, those rewards, they're just going to remain the same. Nothing happens to the to the rewards. But if you are setting up the value of gamma to 0.9, then see what happens. Look at the rewards now. Okay, the rewards actually change because the gamma plays a very important role. Okay, in your reward selection. Okay, so remember I said that at the S step, you will actually have to find the max of the Q state. And what the Q state is, let me just tell you this, what this is. Let me tell you what this equation is. Remember, we're going to be here and we're going to get the average. Let's get the Q value from here, QS prime A. Meaning, so we're going to have the values, right? Like values here, V1 A S prime, V2, S prime, blah, 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 all possible. That means you're basically looking at the value of each child node, right? You're going to get the value of, you're looking at the value of each child node, and you're going to get the weighted average, right? Weighted average, the probability times V. If you remember in expect-max search, we had the probability times like P1 times V1 plus P times P2 times V2, so on and so forth. We had that equation, right, in expect-max. And where are those probabilities coming from? Which is right here, S prime T from current state taking an action to going to S prime. So that's the transition matrix. You're getting basically those probability values from the transition matrix, and you're multiplying the value of each child node, right? Of each child node. That's exactly the expect-max search, isn't it? P times V. And you're just doing the weighted average. You're doing the summation. Does that make sense? The probability. So the probability, we're getting the probability from the transition matrix, right? P1 times V1 plus P2 times V2, et cetera, et cetera. So from here, we're going to say there's a certain probability that we get to this state, right? There's a certain probability we can get to another state, right? So we're going to get the probabilities, and we're going to multiply it with the values that each node has. That's all what we're doing in expect-MX, right? So far, we're using expect-MX here. But what we have to include is we're going to have to include the reward, right? The immediate reward that we're going to have, which is RT plus 1. So that's the new term that we have included in our MDP, the immediate reward. Before this, everything was just expect-MX. Reward, but then we're also going to see how short or far-sighted we are. So we will have to multiply V with gamma value. And that's where we get this value. So if you remove this part, V star S prime and this probability transition matrix is just expect-MX. Our Q state is just the expect-MX. But what we have now in here is that RSA S prime. Taking like your current state, you're taking a specific action, you're getting into a new state, and what is the reward that you're going to get? So from the class dynamic example, remember the R values, the red font. That's what you're going to get, and then you're going to multiply your V with gamma, and that gets us to the Q state, which is what we're going to talk about in quite detail from next lecture. Okay, and what we will have to do is, if you just simply plug this back, the Q state in here, we'll just look something. Okay, so from Wednesday and from next week, we're gonna talk about several problems, or I'm going to show you guys the algorithm that uses this Q value to solve real world problems. Like a lot of new real world problems that we're gonna solve using MDPs and reinforcement learning. Okay, so unfortunately we were a little, late. I didn't have